Hey guys, this should be 17.1 through, I think it's through 17.5 or somewhere around there. Yeah, through 17.5 notes for physics. And just a few big concepts that we need to come to common ground as we come to understand. Yeah. All right, so here we go. We're going to start to talk about the concept that you and I commonly refer to as voltage. When we talk about voltage, we need to understand that it wasn't originally called that, and so we have to come at it from the perspective of its traditional name and why is it called what it was called. Because honestly, the name voltage is so commonplace in our vernacular, and we use it to talk about the voltage on a battery, lots of things. And yet so few of us really understand what we mean when we say that. So it's important. This is one of those places where we can really come to understand how words, especially initially when we're first discovering about things, they really mean what we think we're seeing. And so what you need to understand is that the term voltage wasn't used to describe what we call voltage for a very long time. It was actually called potential difference. Okay? And it has to do with this idea that if we have a bunch of positive charge piled up over here, okay, maybe on a metal plate or something like that, and over here we have a whole bunch of negative charge, or we'll call it the absence of positive charge over here. And so we have, if we were to put a positive charge loose outside of that plate, close to that first plate, we know that the electric field lines would point in a way to push our positive charge, right, towards the negative and away from the positive. Well, if you were to put a charge there, positive or negative, and watch its movement, you might be a little confused and say, why is this moving? What's causing this physical movement? Because you've got to remember, scientists back in the day, they were looking at movement of objects, and we came up with ideas like gravity. We said, why does it seem like there's a sideways gravity, or that there's something forcing it somewhere else? Where's this force coming from? And so it was called the electrostatic force, because it was built off the concept of buildup of charge. But we wanted to talk about how much force would be applied to this charge. And we learned a little bit about that in chapter 16, how depending on the size of the charge, you'd have a different result. Well, what was recognized and understood was that the forces would cause acceleration much the same as gravity causes acceleration. And so the decision was made, or the conversation was talked about, that there would be essentially like a rock falling off the edge of a cliff, that there would be potential energy that would convert through work done by gravity, right? Work by gravity would be done and convert that into kinetic energy. Okay, and so as we can see that that as we go from potential energy to kinetic energy, we have an increase in velocity, and we would see very similar behavior as this charged particle moves from the positive to the negative, almost like an object in free fall. And so first thing was, we wanted to talk about this idea of electric potential energy. Obviously, keeping that positive charge close to the other positives would require a stored energy. It would be like pushing, think about a rubber band or a spring, you've compressed it, now you want to hold it there. To do that, you're going to have to acknowledge that there's some potential energy stored there, and that when you release it, it's going to be able to create or change into kinetic energy. And so we recognize, first off, there's some potential whenever we bring charges close to each other. And along that same lines, we have what's called potential difference. When we talk about the difference in potential energy, essentially, it wasn't exactly energy that we were measuring, but there's a relationship that we're saying, hey, there's a bigger potential, right, over by the positives than there is over here. This guy over here has less potential. And when we talk about the potential difference, okay, that difference in potential, that is what we commonly refer to as voltage. Okay? It's about the difference in potential from one position to another. So if these both had positives, right, if these were both equally positively charged plates, then there would be no difference between one plate and the other, and therefore there would be no voltage between the two. So you have to understand is that getting to zero voltage is not, necessarily what you might think of. It just means we have a level plate. But really, zero voltage is about having no difference between the two plates. They could both have a lot of negative charge, or both have a lot of positive charge. But if they're balanced, we have no voltage. And so that's the key idea of potential difference versus voltage. When we say voltage, we're saying that there is a difference between the two terminals, or two plates. All right, let's jump down and talk about a couple of formulas. If we wanted to talk about the work done by an electric field or because of a voltage, the formula that we walk away with, if we're real careful here, is that when there is a potential difference between two positions, the voltage difference or potential difference between point B and point A, okay, so you got point B, you got point A, okay, the voltage or potential difference between them will equal the negative of the work done to move a charge. Now this is important. That negative has to do with directionality. Are we moving a positive towards other positives or a negative towards other negatives? What you have to remember is, let's say I have a big positive pile of charge over here, right? And I have negatives over here. If I want to take a positive charge and push it to the left, well, I'm going to have to do a lot of work. And that's going to tell me about the potential difference or the voltage between the two spots, between points A and point B. So this first formula, V, the difference in voltage or the potential difference is equal to work divided by the charge that's being moved. Not the charge on either specific plate, but the charge that we're moving. Again, we use a little q to represent the concept of a test charge. And so when we measure the units for electric potential or potential difference, it's in joules per coulomb, and that has a special name of a volt, named after Alessandro Volta. And he was one of the first to invent the electric battery. We use a capital V for it, and we can let one of the two terminals of any battery be 0 volts, and the other one will be increased or decreased from there. Because really what we want is the potential difference. We don't really care about the specific voltage on one spot. We want to know about, the difference between the two. All right, if we keep coming down, there are a couple of, and here you can kind of see this concept of falling objects, more potential, different voltages. A couple other formulas or relationships you need to understand. There's a relationship between electric fields and voltages. In other words, a potential difference between two plates will create an electric field. You can see that here in this diagram here, where we have a 50 volt difference at 5 centimeters, and that's going to produce an electric field that's pointing from left to right everywhere inside these plates. Okay, so if we wanted to know how strong is that electric field that we're going to create, there is another relationship there, and the electric field equals the negative of the voltage difference or potential difference divided by the distance between the two plates. So that's another equivalence for our electric field, but it's also another way to find voltage. If I know what the electric field strength is between 2 points and their distance, I should be able to figure out the voltage there as well. So a couple other things. Because you look at this unit right here, V over D, would be volts per meter. So that is an okay unit to use for electric field, and so is newtons per coulomb. Essentially, they are synonymous units. You will see those placed into problems interchangeably depending on the numbers you're given and the values you're using. And so you should be comfortable answering your electric field strength with either newtons per coulomb or volts per meter. It won't matter. You might see me write one versus another in the notes or in the text as a solution, but that's totally based on what units did I use to get my answer. If I'm using a voltage and a distance, I should probably answer in volts per meter, though it's no different than answering in newtons per coulomb. And if you're not sure, all you have to do is take what is a volt, what is a newton, what is a coulomb, and convert their units, and you'd see that they are identical in value. Other things that you might want to understand. So Joules are really big when we start talking about battery storage. Like a joule of energy in a battery is a ton. And so we have other measurements that we like to use sometimes to size it down to a smaller scale. And so we have this conversion. We have what's called an electron volt. Now, keep in mind, it's not voltage. It's not. It's energy. Okay, it's a different unit for energy. Like calories are a different unit. We use that for food consumption, whereas we use joules for maybe electricity or solar panels. We'd use those for measurements of energy there. Here, the electron volt is the energy unit we're going to introduce. And it really is based on the concept of taking one electron times 1 volt. And so if you're ever given electron volts or asked for electron volts, this is your conversion factor between joules and electron volts. Last two things we need to talk about. If you want to know about how much potential there is due to a pileup of charge, we call it a point charge. Right, so I have a bunch of charge piled up somewhere. Let's call it a bunch of positives here. Okay, there's my pile of charge, and I want to know how the voltage, right? So over here, if I come over here, okay, to a point, there's no charge built up here, so there should be a difference or a voltage between these two. Anytime you build up charge in one spot and you don't do it equally somewhere else, there's definitely going to be a voltage created between them. And so we want to talk about, think about it, when you're getting off the trampoline, you've rubbed your socks on the trampoline, now you've got built up charge on you. The earth or your friend might not have done the same thing. And so because you're not at the same voltage, there is because you don't have the same charge buildup, you're going to have a voltage difference. So we want to know how much voltage difference that is. It's going to depend on how close you are. If I get really far away from you, the voltage is essentially 0. So we end up with is this formula. The voltage will equal K, which we know is 8.988 E9, times Q, the point charge, divided by the radius. It has it written a little differently here. Don't worry about it. I like just having it written as one big fraction. It won't matter how you write it, though. But that's something that we can evaluate voltage based on distance from a point charge. We build up a bunch of charge there. And then one last thing, and I don't know that it's in here, but one last thing we kind of need to talk about. It's the last question in your assignment number 16. When you're looking at question number 16 in this assignment, you need to understand that the potential energy that exists between two charges, okay, two charges, okay, will equal K Q times Q over R. Now, this looks a lot like this voltage equation, and what we're doing is we're taking that voltage and we're timesing it by the extra charge. Okay, if you guys remember, work is equal to voltage times Q. The formula was V equals W over Q, but if we rearrange this, we'll end up with work done, which is often synonymous with the potential energy, or how much energy stored, is equal to the voltage, which is this formula up here, times the charge that's being moved around. And so that's where we get this extra Q in here, okay, that guy right there. But if you have that information, I think the question 16 asks you to do sort of a before and after, where you start by doing the the change in potential energy or the work done. If you calculate the amount of potential energy that exists initially, and you do the potential energy that exists after the movement of the radius, then you can determine how much work was done because there's a change in potential energy. Okay, I hope that gets you what you need to be successful today. Check the notes, check the solutions, do the best you can, and let me know when you get back into class. All right, we'll see you.